All right, today we're going to talk about relations and functions. And I think a really good overview of this is to think about relations and functions in terms of going from very general to very specific. So I've given you a Venn diagram, and hopefully you're familiar with these and you know that the outermost circle or bubble is the most general. And as you go inside or move inward, your terms get more and more specific. So here are the different terms that I want you to put in. The most general term that we're going to talk about today is a relation or relations. And relations are essentially a relationship between two quantities. Usually those are an x and a y value, but it doesn't have to be in order to be a relation. But basically anything you can graph on a coordinate plane would be considered a relation. So as we move more inward, relations that are more specific can be given the term function. So functions, a function is a type of relation, but it's a type of relation in which every x value is paired with only one y value. So sometimes you're going to hear different terms to describe x values. Sometimes x values are called inputs, sometimes they're called domains, sometimes they're called the independent variable. Every y value is sometimes, y values are sometimes called the outputs, the range values, or the dependent variables. So anytime you have a relation in which every x value is paired with only one y value, then it's a function. Write this down as well. There's no pattern needed for a function. Another thing to think about is go back to the cyber chase episode that you watched, and functions are relations where you know the outcome, where the outcome is certain, whereas relations that are non-functional would be ones in which you're not certain of the outcome. In other words, you're not sure if when you push button number 1 on the frog, if he's going to jump 1 time or 5 times. But if the situation is functional, then you do know for sure how many times the frog is going to hop when you push a certain button. Then we're going to talk about 3 very specific types of functions this year in Algebra 1. So for today, just be familiar with the terms. We're going to talk about linear functions, we're going to talk about quadratic functions, and we're going to talk about exponential functions. Now I want you to notice, once we get into these specific types of functions, there is a specific pattern needed in order to make each of those specific types of functions. Now, for right now, I want you guys to just write this part down, but we're going to talk about it in detail on the next page. So for a relation, a vertical line drawn somewhere, sometimes multiple places, sometimes only one place, but a vertical line will pass through more than one point at some place on the graph. Whereas if you're dealing with a function, that a vertical line drawn anywhere on the graph won't ever pass more than one point. Okay, so let's talk about some examples. We want to do examples of tables where some are functional and some are non-functional. All of these are relations. Why? Because you have a relationship between two quantities. So let's talk about which ones are relations that are also functional. Think again about the frog. So if you push the button labeled 0, the only output value you're going to get is a 10. If you push a 1, you're only going to get a 12. If you push a 2, you're only going to get a 14. If you push a 3, you're only going to get a 16. And 4, you're only going to get an 18. And so this is a relation that is a function. All right, let's go on to the next one. Now, that first table was nice and neat, and all of those y values increased by 2 every time. For example 2, notice these are all crazy. They're jumping around. There's no pattern. Everything's really messy. But notice if you push a 0, you're only going to get a negative 3. 1 will only give you 12. 2 will only give you 18, and so on. So even though there's no pattern, this is still a relation that we can call functional, or it's a relation that is also a function. Now let's look at example 3. Here, if we push 0, we know we're going to get a 10, but notice for 1. Sometimes when you push 1 or your input is a 1, you'll get a 12, and other times you'll get a 14. Think about the frog. If you sometimes get 12 hops and sometimes get 14 hops, then the outcome or the output is not consistent or reliable, so this one would only be a relation. And finally, here, notice if we get 0, there's 10 hops. Notice we see a whole lot of repetition here, but every time you push a 1, you get 10. Every time you push a 2, you get 10. Every time you push a 3, you get 10. Every time you push a 4, you get 10. So we don't care if there's the same y value over and over and over. What we care about is if you have the same x value that goes to different y values. So for example 4, even though it's kind of a weird table, it's still a relation that we would call more specifically a function. All right, now if we sometimes you'll just see lists of ordered pairs, but again, you can rewrite these in a table form. Remember the first letter or the first number is your x and the second is your y. So what you want to look at is there a time where 2 will yield something other than a 3? And if you notice, it doesn't. So we have certainty with this, so this is also a function. Okay, now for this next example, notice right here. You have a 3 that sometimes gives the input of 3, that the output is 8, and then other times an input of 3 gives you an output of 2. There is no reliability here, so we would call this a non-functional situation, or in other words, a relation only. All right, so let's go to those bubbles. These diagrams are called mapping diagrams. So sometimes you'll have like a box or a circle or something like that, but you'll have, if it's not labeled, always assume that the left bubble is your x and the right bubble is your y. I would recommend changing these into a table. So what this is saying is that an input of 1 gives you an output of 5. So if we said that this is our x and this is our y, 1, 5 is one of the points, 2, 5 is one of the points, and 4, 8 is one of the points. Now we can ask ourselves, is there certainty? And even though 5 is repeated twice, it doesn't mean that we can't control this relation. When we have an input of 1, it only gives an output of 5. When we have an input of 2, it only gives you an output of 5. So we would say that this relation is also a function. And finally, let's look at this one. So again, if we were to rewrite this as a table, 2 has an output of -8, 2 also has an output of 0, and 2 also has an output of 0.2. So there's no certainty in this relation, so therefore it is non-functional, or it's a relation only. All right, I want you to notice the situations where there was a relation only were the ones where you have, like when you made your table, you have repeated x values. So like there's a repeated 3, for example, 6. The 2 is repeated, for example, 8. The 1 is repeated, for example, 3. So I have a really dumb way to remember that. So I always tell students, have you ever had a relationship with someone and you were having issues in that relationship because you had an ex-boyfriend or girlfriend that kept coming back and just kind of interfering with the relationship? And probably what happened is it made your current relationship not work very well. It didn't function very well. So dumb way to remember when you have a function or only a relationship is this statement. For a relationship to be functional, there must be no repeating x's. So kind of silly, but hopefully it sticks in your head. All right, finally, we're going to go on and we're going to talk about how can you tell from a graph whether you're dealing with a function or only a relation. So the key here is identifying repeating x's. So I want you to notice, for example, 10. If I identified the point right here, that point would be 0, 2. And if I identify the point directly below it, that point would be 0, -2. And at that moment, hopefully you're going, oh, it's not a function because we have repeated x values. And that is absolutely true. Now I want you to think about how those points are oriented with each other. Notice they are oriented vertically. So there's a test that you're going to hear about. And we actually talked about it on the first page. It's called the vertical line test. And what it says is that if you can draw a vertical line anywhere on a graph and it passes the graph more than one place, then it is not a function. Okay, so this one we would say it fails the vertical line test. So if it fails the vertical line test, it is not a function. So we would say this is a relation only, or we could say this is non-functional. Okay, so for that first example, notice no matter where we draw a vertical line, it only passes the graph in one place. So because of that, it passes the vertical line test, and this one is a function. All right, let's go on to example 11 and use the vertical line test. So if we draw a vertical line, we could draw multiple vertical lines over and over and over and over and over and over and over, and it doesn't matter where the vertical line is, it only passes the graph of that relation in one place. So we can say that the relation is more specifically a function. And finally, example 12, notice we can draw vertical lines all over here, but as soon as we draw vertical lines here, we're able to pass the graph in more than one place. So if any point along any part of the graph, a vertical line passes the graph more than once, this relation is only a relation. It's non-functional. So notice I'm kind of using different terminology here, and all of the terminology I'm using is legitimate. So you can say that this is a relation only, or you can say that this is non-functional. All right. So let's get down the rule for the vertical line test. And the rule is if a vertical line drawn anywhere on the graph passes through more than one point, that's the key, then the graph is not a function. Why? Keep that in mind. That vertical line passing more than one place identifies repeating x's. And repeating x's means that the graph is not it's not predictable. It's not certain. If you have an x value, you're not sure what the y value is going to be because there's more than one. So keep that in mind. Vertical line test is a bit of a trick, but if you remember the repeating x's and whether the outcome is certain, that should help you. Okay, we're going to move into a little bit of a different topic, but we're going to talk again or still about functions. But what we're going to do is we're going to continue practicing writing functions from practical examples and then graphing those. So Louie has a $55 Juiceland gift card to use for $5 smoothies. How much money Y does Louie have remaining on her card after X smoothies? Some of you will automatically know what this equation is, and some of you won't. So for those of you who don't, let's do a process column. We're going to pick some numbers and see if we can come up with a pattern. So let's just say that Louie hasn't bought any smoothies. Well, think about how much money she's going to have in her card. She's going to have $55. If she buys one smoothie, she's going to have $50. Well, think about how you got that. You took $55, which she originally had, and you're going to subtract $5 from it for the one smoothie. If she does, let's say, 3 smoothies, then you're going to say she started off with $55 and then she spent $15. How'd you get that? You do 5 times 3. Let's say she buys 10 smoothies. She's going to start off with $55 and then she's going to spend $50. How'd you get that? It's 5 times 10 and she'll have only $5 left. So for the 3, she would have had $40 left. So we can back up. Again, you can see a pattern fairly clearly right here. If you'd like to fill in the pattern a little bit more clearly on the other lines, you can say that this is 5 times 1, and you could say this is 55 minus 5 times 0. And hopefully at this point you know the pattern. So if we don't know how many smoothies she buys, you can say that it's $55 minus 5 times however many smoothies she buys, and that's going to give you your y value. Okay, so here's what we've done. We figured out a function rule. The rule is y is equal to, so y is the amount of money she has left on her card, and it's equal to 55 minus 5 times however many smoothies she buys. Okay, so this, we'll see in just a second, is going to be a function. Let's talk about why. Well, however many number of smoothies she buys, there's really only one possibility for how much money she has left on her card. So that's one way to look at it. The other way to look at it is let's graph it and see what it looks like. So our first ordered pair is going to be 0, 55, and then 150, and then 340, and so on. So if we did 0, 55, it's going to be right here. And then 150 is going to be right here. And then 340. So 3 and then 40 would be right here. And then 10, 5 is going to be right here. And here's the deal. Notice those are good numbers. We could, in some instances, connect those dots with a line and have an accurate graph. However, think about this. If you connect the dots with a line, what you're saying is, if we zoomed way into here, you're saying that she can buy 0.1 smoothies and spend that much money, which doesn't make sense at all. So what do we do with that? So if we were to be really, really, really specific here, and I won't always require this, but I'm going to do it with you guys today. I want you to notice that for every smoothie that Louie buys, she's gonna lose $5. So losing $5 would be jumping down to here and then going over 1. So now what we can do is continue to fill in the missing boxes. So from this point right here, we can go down 5. So down 5 is to here and over 1 and continue. And now continue down 5 and over 1 and down 5 and over 1 and down 5 and over 1, and we can keep going until she's completely out of money. So let's talk about this graph. First, it's a function. Why is it a function? Well, you can say it a lot of different ways. You can say that for any number of drinks or smoothies she buys, there's only one possibility for how much money she has left on her card. You could say from the graph that a vertical line drawn anywhere on the graph will only pass 1 point and 1 point only. Or you could say from the table that if you plugged in every possible x value in this first column, there would not be any repeating x's. So it's a function. Okay, let's do that next one. And we're going to continue practice writing function rules from practical scenarios and then graphing those. All right, so Franklin is going on a road trip to San Francisco. He's already driven 25 miles and is driving at a constant rate of 50 miles per hour. How far, y, has Franklin driven after x hours? So let's do this. So we'll have our x and our y, and then we'll leave room for a process. So let's just say at the very beginning of his road trip, how far has he driven? He's driven 25 miles. That's what the question tells us. After 1 hour, Franklin will have driven, he started off with 25, and then he's going to drive 50 miles more, so plus 50, for a total of 75. Let's say after 5 hours, it's going to be 25 plus 50 times 5. So 25 plus 250 is 275. Let's say 10 hours. After 10 hours, he's going to have driven the 25 that he started with, plus another 500. How'd you get that? 50 times 10. So then he'd have 525 miles total. And we can continue. Now notice we can see a pattern, and we can go back and fill these in. I could put a 1 there. Here I could do 25 plus 50 times 0. Now we see a pattern, and we can say our general rule, if he goes x hours, is 25 plus 50x. And that's going to give you your y value. So our function rule, y is equal to 25 plus 50x. Now let's go and plug these numbers in and graph our function. So at the very beginning, he's gone 25 miles. Now be careful here. This is counting by 20. So there's 20, 40, 60, 80. So 25 miles, we're going to just do our best on this graph and say it's about right there. After 1 hour, he's gone 75 miles. So 75 miles might be somewhere like this. After, let's see, at 5 hours, he's gone 275. So 5 is right here, and then 275. So this is 220, 240, 260. This would be 280. So we're going to go about over to right here. And then we did 10 hours. So 10 is right here, and he will have gone 525 miles. We're actually going to be off the graph. It's going to be somewhere like that. Now, let's talk about those in-between points. So what you want to ask yourself is it valid? Could we ask ourselves how long or how far has he driven after 5 hours and 2 minutes? And the truth is that's a valid time. He will actually experience 5 hours and 2 minutes, and he will actually have a specific distance at 5 hours and 2 minutes. So what we want to communicate with our graph is that all of these little tiny in-between points should be included. All those infinite points should be included. So what does that look like? Well, it means that we're going to connect all of those dots with a line. And our final graph will be a line that theoretically is going to keep going on until he reaches San Francisco. So again, let's talk in terms of functions. Is this a function? Yes, it is. We could say that for a couple different reasons. We could say that there's only one place that Franklin can be after 0 hours. There's only one place that Franklin can be after 5 hours, and so on. We could say that if we theoretically filled out this whole table, there would be no repeating x's. Or we can say, based on the vertical line test, a vertical line drawn anywhere on this entire graph, even if we kept going forever and ever and ever and ever, it would only cross the graph in one place and one only. So therefore, it's a function.